Let's start with a moment you've lived through thousands of times without thinking about it. You open your browser, you type youtube.com, you hit enter, and within about half a second, sometimes less, a web page starts loading. Now, somewhere in that half second, something interesting happened. Your browser needed to send a request across the internet to YouTube's servers, and to do that, it needed an address, a real IP address, the kind we talked about in the addressing series, that the network can actually route packets to. But here's the thing. Your browser didn't know that address. You didn't type an address. You typed a name, youtube.com. A name that, by itself, means nothing to the network infrastructure underneath. So before your browser could send a single packet to YouTube, it had to go find the address. It had to ask someone. That process, taking a name and finding the address it maps to, is called name resolution. And the way it works is, honestly, one of the most cleverly designed systems in all of computing. Not because it's mathematically exotic or theoretically complex, but because it solves a genuinely hard coordination problem at a scale that shouldn't be possible, and it does it so quietly, so quickly, that you never notice it's happening at all. Let's build it up from scratch. First, let's appreciate exactly how hard the problem is. The internet has hundreds of millions of domain names. Google.com, Wikipedia.org, BBC.co.uk, and on. Hundreds of millions of them, with new ones being registered every day. Each one maps to one or more IP addresses. And every single device on the internet needs to be able to look up any of them at any time, from anywhere in the world. Your laptop in Birmingham needs to be able to resolve nhk.or.jp, a Japanese broadcaster, without having any prior knowledge of it. A server in Tokyo needs to be able to resolve gov.uk just as easily. Every device, any name, anywhere, instantly. How do you build a system for that? Well, let's think about the most naive approach first, because it's actually instructive. What if there was just one giant file, a master list, that contained every single domain name and its corresponding IP address? One enormous lookup table. Your computer downloads a copy, keeps it locally, and whenever it needs to resolve a name, it just looks it up in the list. Simple, fast, no network round trips required. This isn't just a thought experiment, by the way. This is literally how it worked in the early days of the internet, when the internet was small enough for it to be viable. There was a file called hosts.txt, maintained by a single organization at Stanford Research Institute and periodically distributed to every machine on the network. You needed a new name. You contacted them, they added it to the file, and eventually everyone's copy updated. For a few hundred machines, this worked fine. But then the internet started growing, and the problems became obvious almost immediately. The file got bigger, distribution became slower. By the time your copy arrived, it was already out of date. Worse, every time anyone, anywhere wanted to add or change a name, they had to go through one single central authority. That's not just a bottleneck. It's a single point of failure, a political choke point, and an organizational nightmare, all at once. And fundamentally, the model just doesn't scale. A file that covers hundreds of millions of names, updated constantly, distributed to billions of devices, that's not a file anymore. That's an impossible pipe dream. So around 1983, a computer scientist named Paul Mockapetris sat down and designed something different, something that's still running today, still handling trillions of lookups per year, and still largely working the way he designed it. He called it the Domain Name System, DNS. The insight at the heart of DNS is this: instead of one central list that knows everything, build a hierarchy of systems where each part only needs to know about its own small piece of the namespace. Let's think about what that means. Look at a domain name. Let's use mail.google.com as our example. Read it from right to left, and you'll notice it has structure. There's com, then there's Google, inside .com. Then there's mail, inside google.com. This isn't cosmetic. This hierarchical structure, dots separating levels, is the architecture of the naming system itself. At the very top is something called the root. It's invisible in everyday use. You never type it, but it's always there. Every single domain name on the internet ultimately ends with a dot. Google.com is technically google.com with a trailing dot. That invisible dot at the end represents the root of the entire hierarchy. Everything starts there. Below the root is the first visible level, the top-level domains, or TLDs. These are things like com, org, net, UK, JP, edu. There are a few thousand of them. The com TLD is the most populated by far. It contains hundreds of millions of domain names underneath it. Below the TLDs are the second-level domains, the names you actually register. Google under com, Wikipedia under org, BBC under co.uk. These are the names individuals and organizations own and control. And below those, you can go further, subdomains. mail.google.com has mail as a subdomain of google.com. docs.google.com has docs. Organizations can create these themselves, as deep as they want. abcdexample.com is a perfectly valid name if someone wants to set it up. So the namespace, the full universe of all possible domain names, is a tree, an enormous tree, with the root at the top, branching down through TLDs, through second-level domains, through subdomains, down to individual host names at the leaves. And the genius of DNS is that this tree is also the structure of authority. Every part of the tree is managed by whoever is responsible for that part. The organizations that run com are responsible for knowing what's inside com. Google is responsible for knowing what's inside google.com. Your company controls what's inside your company's domain. Nobody needs to know everything. Everyone just needs to know their own piece, and crucially, needs to know who to ask for pieces they don't know. Now let's talk about who the actual players are. Because name resolution isn't just one thing happening. It's a conversation, a structured, hierarchical conversation between several different systems. The first player is your own computer, or more precisely, a piece of software running on it called the stub resolver. When your browser needs to resolve mail.google.com, it doesn't do the work itself. It hands the question to the stub resolver, which is just a small client library. The stub resolver's job is minimal. It takes the question and forwards it to the next player. The next player is the recursive resolver, also called a recursive name server, or sometimes a full-service resolver. This is typically a server run by your internet service provider, or by a public DNS service like Google's 8.8 or 8, or Cloudflare's 1.1.1. When your stub resolver asks what's the address for mail.google.com, it's asking this recursive resolver. And the recursive resolver is the workhorse of the whole operation. It's the one that actually does the legwork. Its job is to take a question it doesn't know the answer to and go find it by working through the hierarchy one level at a time until it gets a definitive answer. Then it sends that answer back to you. The remaining players are the authoritative name servers, the servers that actually hold the records. There are 3 types we care about in a typical resolution. There are the root name servers, 13 logical server addresses at the very top of the hierarchy, operated by various organizations around the world. These servers don't know the address for mail.google.com. What they do know is where to find the name servers responsible for com. Then there are the TLD name servers, servers operated by the organizations that run each top-level domain. The com TLD name servers don't know the address for mail.google.com either, but they know where to find the name servers responsible for google.com. And finally, there are the authoritative name servers for the domain itself, the servers that Google operates for google.com. These servers actually know the answer. When you ask them, what's the address for mail.google.com, they tell you. Root, TLD, authoritative domain. That's the chain. Okay, now let's watch this whole thing run step by step. You type mail.google.com in your browser. Your browser hands the name to the stub resolver on your computer. The stub resolver checks one thing first. Is there an answer already cached locally? If you or someone else on the same system resolved this name recently, the answer might still be sitting in memory. If it is, great, return it immediately, no network trip required. We'll talk more about caching in a dedicated video later in this series. For now, assume the cache is cold. There's no stored answer. So the stub resolver sends the question to your recursive resolver. Let's say it's Cloudflare's 1.1.1.1. The question arrives. What is the IP address for mail.google.com? The recursive resolver now begins its work. It too checks its cache first. Again, assume cold cache for the sake of walking through the full process. Step 1. Ask the root. The recursive resolver contacts one of the root name servers and asks, "I'm looking for mail.google.com. Can you help?" The root server looks at the name, sees that it ends in com, and says, "I don't know the full answer, but here are the name servers responsible for the com TLD. Go ask them." It returns a list of name server addresses for the com TLD. Step 2. Ask the TLD. The recursive resolver now contacts one of the com TLD name servers and asks the same question. "What's the address for mail.google.com?" The TLD name server looks at the name, sees that the next level is Google, and says, "I don't know the full answer, but here are the name servers responsible for google.com. Go ask them." It returns the addresses of Google's authoritative name servers. Step 3. Ask the authoritative name server. The recursive resolver contacts one of Google's authoritative name servers for google.com and asks, "What's the address for mail.google.com?" This server does know. It looks up mail.google.com in its records and returns the IP address. Let's say it's 142.250.74.165. Step 4. Return the answer. The recursive resolver now has the answer. It sends it back to your stub resolver. Your stub resolver hands it to your browser. Your browser makes the connection. The web page starts loading. All of that root, TLD, authoritative name server, back to you, typically happens in somewhere between 20 and 120 milliseconds, often less. Now I want to pause here and make sure something is clear, because it's a distinction worth understanding. There are two fundamentally different ways a resolver could go through this process. They're called recursive resolution and iterative resolution, and they reflect a difference in who does the work. In recursive resolution, which is what your stub resolver does, you hand the question to someone and say, "I need the final answer, please sort it out yourself." You don't want to be involved in the back and forth. You want one response, the address, or an error. In iterative resolution, which is what the recursive resolver typically does, you ask each server in turn, and each one either gives you the answer or sends you to someone else who might know. You're doing the legwork yourself, taking each referral and following it to the next server. So confusingly, the thing called a recursive resolver actually does iterative lookups. It follows each referral step by step. It's called a recursive resolver because it provides a recursive service to your stub resolver. You send one question, it goes away, does all the iterating, and comes back with one final answer. The naming is a little backwards from what you'd expect, but that's DNS for you. There's one more piece of this we should talk about, and it's actually what makes the whole system viable at scale: the root. The recursive resolver starts every cold lookup by going to the root, every single time. Which means the root name servers are being contacted by essentially every resolver on the internet, constantly, for every cold lookup that doesn't hit a cache. There are only 13 root name server addresses. How are they not completely overwhelmed? This is where the design gets clever. First, those 13 addresses aren't 13 physical machines. They're 13 anycast addresses, a networking technique where the same IP address is announced from hundreds of different physical servers spread across the world. When your recursive resolver contacts root server a.rootservers.net, it's automatically routed to whichever physical instance of that server is closest to it, geographically and topologically. In total, there are over 1,500 individual root server instances around the world. Second, and this is maybe the bigger factor, the root servers almost never have to do much. Their answers barely change. Who handles com? The answer to that question has been the same for decades. So recursive resolvers cache the root server responses very aggressively for very long periods. In practice, the vast majority of DNS lookups never actually reach the root, because the recursive resolver already knows which TLD name servers to ask. In fact, there's a practice called priming, where recursive resolvers come preloaded with the addresses of the root name servers and the major TLD name servers right out of the box. The root is the conceptual anchor of the whole system, but operationally, it's often skipped. Let's zoom out for a moment and look at what this design actually achieves. The problem we started with was, how do you build a lookup system for hundreds of millions of names that works for billions of devices anywhere in the world, stays up to date as names change, and remains fast? DNS solves it by distributing the problem across the hierarchy of authority that already exists naturally in the namespace. Google doesn't need to register every google.com subdomain with a central authority. They just control their own zone, and the rest of the system knows to ask them. A new startup registering mynewapp.io doesn't require anyone to update a global table. They register the second-level domain, they set up their name servers, and immediately the entire DNS system knows how to find them because the chain of referrals will lead to their servers. Changes propagate naturally. New names become resolvable immediately. The load is spread across thousands of servers worldwide, each only responsible for what it knows about. And the whole thing runs, mostly invisibly, behind every single thing you do on the internet. There are, of course, things that can go wrong, and ways the system is more complicated than this clean picture suggests. Resolution can fail, cached answers can go stale. Different resolvers in different parts of the world can give you different answers for the same name. We'll dig into all of those in upcoming videos. But it's worth sitting with the design for a moment before we move on, because it's genuinely elegant. Not elegant in the way that a beautiful proof is elegant. Elegant in the way a well-engineered bridge is elegant. It's a structure that bears enormous weight quietly, that was designed to accommodate growth it couldn't fully anticipate, and that has done so for over 40 years without needing to be replaced. Every time you type a domain name, that whole machinery, root, TLD, authoritative server, recursive resolver, cache assembles itself around your question, finds the answer, and dissolves in the time it takes you to draw a breath.